Hi, I'm Bobby Haig. I'm here with my teammates Johnny Martinez and Nathan Racklin, and we're going to tell you about our project, the Point-to-Point Encryption, Decryption, and Accelerator, or P2PEDA for short. Basically, the device performs encryption and decryption of data that you want to keep secure when you're sending it across a network that is not secure. The extra layer of security that is offered by this product as opposed to a typical encryptor or decryptor is that it uses two different encryption algorithms, AES and Blowfish, and Johnny and Nathan will tell you more specifically about those algorithms later. But basically, the use of the two encryption algorithms offers more security than just using one. Here is a typical use case of the device. User A and user B would each have their own instance of the P2PEDA FPGA, and in order for user A to send information to user B, it would be encrypted by its own P2PEDA instance using one of the two encryption schemes. The ciphertext would be received by the receiving FPGA, and it would be aware of which encryption scheme was used by the sender, but a hacker would not be aware if they had intercepted the ciphertext, which scheme was used to encrypt it. And then the decrypted plaintext can be read by user B, and user B can send information back to user A in the same fashion because each P2PEDA module has both encrypt and decrypt capabilities. So here's a diagram of the internal structure of the FPGA. As you can see, there are modules for both encrypt and decrypt for both AES and Blowfish. And we use the way that we can choose between the two encryption algorithms in a way that both the sender and the receiver know, but a hacker would not know, is by using an LFSR, which is a linear feedback shift register, which is essentially a pseudo random number generator. And if you start two LFSRs with the same seed, then they will output 0 and 1 in a pseudo-random fashion, but in a deterministic fashion. So the LFSR is used to choose between AES and Blowfish by the encrypt side every time it encrypts a message. And the decrypt side of the receiving FPGA will use its own LFSR that was begun with the same seed value to decide or to know whether the incoming ciphertext was encrypted using AES and Blowfish, AES or Blowfish, and it can decrypt in the correct fashion as a result. So the way that we have this running on the FPGA is that we have a host program in C++ running on the CPU of the Z board, and you will see this in action later when we do our demo. But basically, it prompts the user for input, and because the encryption schemes can only handle 128 bits, if the string is longer than 16 characters, then there need to be multiple calls to the encryption and decryption modules. And every 128-bit message is then split up further so that it can fit into the 32-bit FIFO between the CPU and the FPGA. And on the right side is a table of how we use those 32 bits. So now moving on to AES, here is Nathan to tell us about that.
Let's talk about our first encryption algorithm, the Advanced Encryption Standard, or AES. AES is one of the most well-known encryption algorithms. It uses a series of substitutions, permutations, mixing, and key addition to effectively encrypt any data. Decryption operates similarly. It reverses the process of encryption by using inverse transformations. There are two main steps to AES. First, the key expansion step, and then the encryption steps. Key expansion takes a fixed 128-bit key and expands it into a 1,408-bit key. A chunk of the expanded key is used for every encryption round and is called the round key. To begin with, the input message is transformed into a 16-item array with each element containing 8 bits. This array emulates a 4x4 matrix. An encryption round consists of taking the input message, substituting the bytes using various substitution boxes, shifting the rows and mixing the columns of the input, and finally adding the round key selected from the expanded key. The substitute byte step replaces a number of bytes from the input message using information held in the substitution box. The shift rows step shifts each item in a given row an amount equal to its row number. For example, the second row is shifted to the left once, the third row twice, and the last row 3 times. The first row is not shifted at all. The mixed column step mixes each column's values by using matrix multiplication on a fixed 4x4 matrix. Finally, in the add round key step, each individual byte of the round key is added to each individual byte of the message. This encryption round repeats many times to thoroughly encrypt the message. Optimizing the individual encryption algorithm led to two main challenges. One, keeping error use below around 33% while attempting to maximize efficiency. To begin optimizations, all shared variables, like substitution boxes and keys, were declared in the same files to prevent unnecessary storage duplication. Next, the expand key's outer loop was pipelined as it iterates many times. Unrolling was avoided as the hardware duplication was prohibitively area intensive. To allow for best case II, the temporary variable array T was completely partitioned, and the large expanded key array was cyclically partitioned with a factor of 4. A factor of 4 was chosen to facilitate the inner loop bound value, and cyclic was chosen to allow for adjacent entry accesses. These optimizations resulted in a 9.3x speedup for the expand key function. Next, the encrypt function contains one main loop that runs iterative AES rounds. This function was pipelined because, once again, unrolling was prohibitively expensive. To allow for the necessary accesses, the input, key, and output arrays were all completely partitioned, and the state key reference in the AES round was also completely partitioned. This resulted in a 11.43x speedup for the AES main function. As you can see, these are both the latency and throughput values for the pre-optimized encrypt and decrypt functions. The encrypt function had a latency of between 33.04 and 44.84 microseconds, while the decrypt had a latency of between 37.69 and 44.49 microseconds. After optimizing, we experienced a great increase in latency and megabytes per second, yielding a new 16.393 megabytes per second value for encrypt and a 25.078 megabytes per second value for decrypt. Although these final values compared very badly against the benchmark, we're happy to say that at the very least it compared favorably against the benchmark's smallest design.
Blowfish is a symmetric encryption algorithm that encrypts 64-bit blocks at a time. The algorithm consists of two main phases, the key expansion phase and the Festal network phase. It also relies heavily on two components, the P arrays, or the P array rather, and the S boxes. The P array consists of 18 subkeys, and S boxes consist of 4 substitution boxes, each containing 256 entries. During the key expansion phase, each element in the P array is XORed with the provided key. Then, a fixed data block of all zeros is encrypted using the XORed P array and initial S boxes. The resulting ciphertext is then used to update the first two entries of the P array. This process is repeated for all entries in the P array and S boxes to ensure that encryption is key dependent. The high-level purpose of the Festal network phase is to modify the input text by XORing it with the P array and substituting in portions of the S boxes. The Festal network takes 16 rounds for both encrypt and decrypt. First, the input text is separated into two 32-bit chunks. Then, the left chunk is XORed with an entry from the P array. The entry of the P array used is determined by the round number. It is then passed into the Festal function, which substitutes entries from the S boxes into the left chunk. The result from the function is set to the new left chunk. The right chunk is assigned to the left chunk, the new left chunk from the function, XORed with the original right chunk. And then this process is repeated 16 times until we either get the ciphertext or the decrypted text. So all the optimizations that I implemented on Blowfish needed to take up around 33% of each resource. I decided to completely array reshape the read-only initial values of the P array and the S boxes. I array partitioned the updated P array completely as it was only 18 entries. I also completely partitioned dimension 1 of S boxes, which was 4 entries. Dimension 2 had 256 elements, and when I tried to completely partition it, my utilization was way too high. Therefore, I avoided modifying it. So the setKey function was the function actually responsible for doing the key expansion phase. Within that function, I unrolled the XOR P array 1 loop with a factor of 2 and completely unrolled the inner loop XOR P array 2. Completely unrolling both loops led to around 60% utilization for very little speedup. So I also completely unrolled the outer loops responsible for encrypting the P arrays and the S boxes. Within the actual encrypt-decrypt functions, I completely unrolled the loops responsible for executing the Festal network. So my unoptimized Blowfish implementation processes text at a rate of 16 megabytes per second. Due to the symmetric nature of the algorithm, the encrypt and decrypt blocks have the same latency at 0.76 microseconds. The setKey function takes substantially longer at 0.369 milliseconds. I compared my implementation to a paper from 2022 that implemented a Blowfish accelerator on a Z board, and their implementation processed at a rate of 31 megabytes per second. with the encrypt and SecKey functions taking 0.25 microseconds and 0.125 milliseconds respectively. So the optimized Blowfish processes text at a rate of 26.6 megabytes per second. Encrypt and SecKey both experienced speedups of approximately 2x. All resource utilization was under 33%, with LUT utilization being the highest at 29%. Overall, the speed of my optimized implementation came within 18% of the paper, while only using a fraction of the Zeb board's overall resources.
This is our P2PEDA demo. It begins with typing make FPGA into the terminal. We then put in a test hello world. As you can see, it gets encrypted, then decrypted, and then you can see the completed output string. For fun, we then encrypt and decrypt our alma mater song, Far Above Coyote's Waters. As you can see, it flawlessly encrypts and decrypts strings even greater than 128 bits. Finally, we copy and paste a selection of text that may be familiar to you, and as you can see, again, it works flawlessly.
So here we have a summary of our results before and after using HLS optimizations. As you can see from the estimated latency numbers, we expected there to be an improvement as a result of using HLS optimizations. However, unfortunately, when actually running on the FPGA, there was no observable improvement, and that's most likely due to the fact that the bottleneck of the entire system is the 32-bit FIFO between the CPU and the FPGA, and not the encryption and decryption. Both versions achieve a throughput of about 11 megabytes per second. Here we quickly outline some possible improvements, especially the ability to change the keys that the encryption schemes are using dynamically at runtime. Thank you so much for listening to our presentation.